Okay, welcome back everybody. So we're moving on to the statement of the spectral theorem for Hermitian operators, and before I actually get into it, I do want to comment that I was having a hard time deciding if I should even include this in an undergraduate text because there's not really a concise way to formally make the statement of the spectral theorem for Hermitian operators to undergraduates. It really, to give this statement precisely, we require kind of 2 semesters of real analysis, complex analysis as well, and maybe even 1 semester of functional analysis. So there's a lot of deep math going on behind the scenes in the real statement of the spectral theorem for Hermitian operators. I've tried to sidestep it with the way that I have described our theorem, and you'll see that there's a lot of random parts that get included here because that's me trying to sidestep a lot of this higher level math that makes it work. So if it seems like a little bit vague or contrived, there's reasons for it. I would rather try to make it not as strong of a statement with the expectation that you can understand it than me to make the perfect statement that you would see in a graduate text and have it go completely over everyone's heads. I already understand it's probably a little bit going over some people's heads, but I think it's accessible in its current form, and I don't think I make any false statements. I tried really hard to weaken it without making any false statements, but keep this all as a caveat. If you find this really interesting and you want to learn more, you probably have to take a couple entire courses worth of math to learn enough more, which would be 2 semesters of real analysis, 1 semester of complex analysis, and even perhaps a semester of functional analysis. So this is really a deep theorem that needs a lot of preparation. I know when I took a functional analysis course, we covered this a little over 2/3 into the semester, so I was as a graduate student. So it's definitely a theorem that shouldn't be taken lightly, and if you want to use it in reality, you can either take the statement that I give as true, that's maybe how a lot of physicists see this theorem, or you can go ahead and take 3 more semesters of math to really understand what's going on. So I did just want to caveat that. So if you know the actual statement of all of this and you think that my statement is weak or maybe a little bit false, don't leave a comment. I'm aware, but we're just going to try to get by with something that's accessible to undergraduates. So let's recall kind of our 3 from the last section, 3 things we defined. We defined it a Hermitian operator as one for which this was true. We could also call this symmetric. Symmetric are Hermitian operators on real vector spaces instead of complex vector spaces. So this was Hermitian. And then we had unitary operators, which satisfied that they left inner products invariant. And we had diagonal, or really multiplication operators, which would take a function and multiply it by another function. And the spectral theorem is a combination of all 3 of these. It really says that to each Hermitian operator, there's an associated unitary operator and its inverse, as well as a multiplication operator, for which L equals U inverse DHU. So this is our version of diagonalization for operators. And let's actually scroll down and see how this needs to be stated, because unfortunately it has to be stated in, like I said, originally a somewhat weak way. But we're going to give ourselves L, mapping a vector space to a vector space, and we're going to assume it's Hermitian, which means it satisfies exactly what I said earlier. But to get away with what I want to get away with and describe it to all of you, I do actually have to define a subset of the vector space, or a subspace of the vector space. And this is really the subspace, which is spanned by VEIG. This is the subspace constructed from all linear combinations of eigenfunctions of L. So the problem is that L may have only 7 eigenfunctions. Probably not, but in some cases it may have only 7 eigenfunctions, even though V is infinitely has infinite dimension, and we can really only make this statement about the space of that's constructed from linear combinations of the eigenfunctions. So we kind of have to restrict ourselves to the space of linear combinations of eigenfunctions, which I define here, and I define this nice and formally. What do I mean by that? I'm saying it's all f's in my original domain, for which the f equals a sum of, this is a collection of coefficients depending on each eigenvalue of L. So I take every eigenvalue and I assign that eigenvalue a coefficient, and then I multiply that coefficient by an eigenfunction, and I sum all of the eigenfunctions together. So as long as f can be written in that form, where e lambda is an eigenfunction, e for eig. And actually, I do require that the sum of all of the coefficients squared, if I sum over all possible eigenvalues, that does have to be a finite sum. So a little bit of caveats on kind of the space that I can actually look into here. And then I'm going to define L sub eig, so L eig is really the restricted operator that only takes these linear combination of eigenfunctions. It takes that space to itself, of course defined just by L, how L would be defined. And if I look at that restricted operator, once I restrict everything to that restricted operator is going to admit purely real eigenvalues. So this feels very much like the spectral theorem for matrices. A set of orthonormal eigenfunctions still feels exactly like the spectral theorem for matrices. And the way I write this set down is E sub lambda, and then I say lambda is in the point spectrum of L. And so I'm saying it's parameterized by their eigenvalues, right? So each eigenfunction is associated to its eigenvalue. And then it admits a diagonalization of exactly the form we wanted out of our spectral theorem. And so this diagonalization actually takes a better form. It's more similar to the spectral theorem for matrices, where we have our unitary transformation and its inverse. But then the diagonal, it's not even a diagonal operator where that's a function. This is the diagonal operator, or multiplication operator corresponding to multiplication by each eigenvalue. And when you think about the spectral theorem for matrices, that's really what went on in the middle as well. The diagonal matrix D along the diagonal had every eigenvalue associated to the eigenvectors, right? So this diagonal or multiplication operator is just going to multiply every term by the eigenvalue. And in fact, you can define, we don't get, U and U inverse to be matrices, right? Everything we're dealing with is an operator here, so we have to be a little bit more clever and say that U as an operator is defined on a function f is just computing the inner product of f against e lambda. And of course, that's the inner product in the v eig space, which is the same as the inner product of v. So we're going to take the inner product of a function against the eigenfunction associated to lambda, and that associated to lambda, that's going to be the argument of the new space w. So whatever this lambda is here, that's the eigenvalue, and that's really the argument of functions in this space w. So that's where u takes you. It takes you from a function space to a new function space where the argument of the new function space is an eigenvalue. And it does that with inner products. And u inverse takes a function in this space w, and it reconstructs it in the space v eig just by taking whatever function it's acting on, f hat, and it's going to assign those eigenvalues, lambda, to f hat. It's going to multiply them by each of the eigenfunctions and then reconstruct by summing over all lambda in the point spectrum. So this is really a reconstruction of f in v from f hat in w. Okay, so that's really what's going on with u and u inverse. You first deconstruct it into each of its eigenvalue terms, and then you reconstruct it with u inverse. And then d, as I mentioned, just multiplies by lambda. Okay, so if I want to write this out, what does that actually look like? This looks like the sum lambda in sigma p L of the, so let's think about it. What does u do? U takes f and it acts it against the eigenfunctions. And then d multiplies everything by lambda. And then u inverse reconstructs all of this against e lambda x. So this is how we want to think about. This is kind of the spectral decomposition of the operator L, as long as L is Hermitian. And that's what this theorem states, is what I have just highlighted for you, is that L equals that specific sum, where you can compute inner products and then reconstructions. So that's a statement of the theorem. I already started this video with so many caveats, and I have explicitly in the book so many caveats as well. Like I said, the true theorem is a more powerful theorem, but you need to know so much math to make it work that I just can't cover it here. So instead, I've got a bunch of caveats here. Caveat number one, let's define the vector space W. Vector space W is defined as functions, but I'm giving the name C for coefficient here. They're coefficient functions, and they map the point spectrum of L into the complex numbers, and they have to be square summable. This is kind of like what we've already seen with v eig. Okay, so that's the space L, and it has an associated inner product where if I multiply two functions in this space W, Then the inner product is defined as the one function times the complex conjugate of the other function. Then we're going to sum over all of the lambdas in the domain. So this vector space is often denoted by little L2 of sigma p of L or capital L2 of sigma p of L to denote the definition of square summable sequences or square integrable functions respectively. Okay, so little L always means sequences, big L always means functions. And now there's a huge caveat with every time you've seen this summation notation here. Summation, summation. And this actually goes all the way back to when I described separation of variables methods, where summations can be summations, but they can also be integration. So whether, capital sigma means summation or integration depends on if sigma PL is continuous or discrete. Discrete meaning isolated points, continuous meaning intervals, right? Real valued intervals versus real valued isolated points. You sum over isolated points, you integrate over intervals. And so it's vague until you discover what sigma p of L is, what the point spectrum of L is, until you discover what shape that takes. If it's discrete or continuous, you don't actually know what form this sum takes. That could be an integral over an interval, or it could just be a sum over all of the point spectrum. So you have to be clever. That's what I specify here, right? So it's an integral, it's a sum. In fact, it could be a combination of an integral and a sum, because sometimes you may have sections of the point spectrum which are intervals, and other sections of the point spectrum which are discrete points, and you have to integrate over the interval section, and you have to sum over the discrete point section. So it really just depends on the nature of sigma p. And once again, this higher level math kind of takes that into account for you. But in the way I state it, you have to be clever. You just have to find sigma p and realize, is this a collection of points? In which case, you just take a sum, or is it a collection of intervals, in which case you integrate. And then that actually plays a role with the definition of what it means to be orthonormal when I get to statement 2 here, a set of orthonormal eigenfunctions. Those mean two different things depending on if it's a sum or if it's an integral. When it's an integral, what it means to be orthonormal is that the inner product of the two of them is the delta function. The delta functions are identity with respect to integrals. So that's what it means to be orthonormal when we have integration. And when we have summation, it means kind of what you'd expect with orthonormal for vectors, where it equals either 1 or 0, depending on if lambda and mu are the same. So you just got to keep both of those two in mind. So that's 2 of my caveats. There's actually 3 more caveats, lucky us. The third caveat says that, well, there's not really anything special about each lambda, right? The way I state the theorem, it kind of looks like there's only going to be, one coefficient corresponding to 1 lambda here. And that's not true, because some lambdas may have more than 1 e sub lambda associated in them. Okay, so what does this actually mean when I'm computing this sum and it looks like I only have 1 instance of a lambda in there? What that actually means when I'm computing a sum and I only have 1 instance of lambda is that actually the term c lambda e sub lambda, or f hat lambda e sub lambda, is an element of the eigenspace corresponding to lambda. So what you actually do is that collection of eigenfunctions, which may all correspond to the same lambda, so all eigenfunctions same lambda, then c lambda e sub lambda is really, it's in this space of all sorts of sums over all, call this c1 or ci lambda e lambda I, and you're going to sum over I. So it's one of those elements where you can take a sum of all of these spans of eigenfunctions. Now, that won't play a huge role, but it certainly does in some situations, because like the Fourier series, there's only one basis element for every single eigenvalue, but in other cases, there's like 5 basis elements corresponding to the same eigenvalue. So you just have to be clever and realize that that's referring to some linear combination of all of those basis elements corresponding to that value lambda. Fourth caveat, the vector space VEig, and like this is something that looks explicit when I state it, it may be a strict subspace of V. Okay, that's not, unheard of the way it's defined. It's certainly defined as a subspace of V. But you just want to be careful in that it's a strict subspace. And in reality, what we want to do is we want to close subspaces. And I just can't get into what it means to close vector spaces to make them complete. What you would really want in a lot of situations is that this VEig, if you closed it, take a couple courses in real analysis to figure out what that means. If you closed the space, you would want it to be equal to the original space, which under a closure, the original space ends up being a Hilbert space. So you want all three of these to be the same. It is the case in a lot of situations. That's what this final caveat is. It says that, okay, you want all three of these to be the same. It turns out in a lot of cases they are the same, but you need a couple more semesters of math to be able to actually prove that they're the same in a lot of cases. And so the physicists, when they take a lot of math courses, but they have to take kind of really important physics courses that use the math, they often always assume that it's true. And that's okay. You can get away with a lot by assuming it's true, but mathematicians do sometimes run into cases where it's not true, and that can be some big problems. So just keep it in mind, this may or may not be true. You want it to be true, because that's kind of what we mean when we solve a PDE with these methods, is that this is true. But you need a couple more courses in math to show that that's the case. So, if you're a physicist, you're an applied mathematician, engineer, go ahead and assume it's true. Wait for your mathematics friend to show up and tell you that you made a bad assumption. But, in a lot of cases, just assume it's true. But I won't be. When I write my papers, I do not assume it's true. Anyway, those are all the caveats. I know that most of this video is just introducing a theorem and all of the ways that it breaks. But that's the theorem for you. I do have a proof here. The proof is actually somewhat similar to how you would prove the theorem for matrices. You can go ahead and read it if you want to. It's not too bad if it's on a page, right? So it's not the easiest proof in the world because it makes a lot of strong statements, but it's not the hardest proof in the world either. Anyway, I have this lovely statement that says, gee, this sure was a long buildup for our, quote, diagonalization theorem. Now, how can we use this, right? Because if we don't know how to use the diagonalization theorem, then what have we actually done? So what we're going to do is I'm going to show you that we've actually been using it implicitly the whole book long. That's in the next example, the Fourier series. So it turns out the Fourier series is just a diagonalization. And I hinted on that the first time I introduced the Fourier series. I said, by the way, this diagonalizes the derivative. And nobody really knew what I meant when I said that. But we're going to make that explicit now, okay? So we're going to start with the operator I times the derivative. Now, why did I have to multiply the derivative by I? This is just to reinforce that it needs to start out as Hermitian. And if you didn't put an I there, you wouldn't get something Hermitian. It would be anti-Hermitian. So we just multiply the derivative by I. That's just to make everything prettier so that it works and we don't have to apply any extra theorems. And we're gonna prove or verify that I d dx, when we take C infinity on the 1 torus to C infinity on the 1 torus, we're going to prove that that is Hermitian. So it's easy enough to verify. All you do, as always, is write down the inner product of f and g, where you put the operator we care about. On f, and then you try to show that you can move it to g for free. So what are we going to do is we're going to explicitly write out the inner product in terms of an integral, and then we're going to try to move, right? So what we want to do is try to move this onto g. And it's pretty easy to move the I onto g, right? Because I is a multiplication by a number. Keep in mind, g does have a line over it. So because there's a complex conjugate on g, when we move I over, the price we pay is this little minus sign in front of I. But we can move I over almost for free. The price we pay is a minus sign. The trickier part is moving d dx over. What's everybody's favorite way to do that? It's integration by parts. So anytime you're trying to move derivatives around in integrals, you're thinking integration by parts. So what does integration by parts say? It says that u dv is vu minus v du. So there's my integration by parts happening here. And I've pushed the d dx over to the g term. But the question is, I do have this boundary term showing up right away. That was uv evaluated on the boundary. I'm canceling it out here, and some of you might be wondering why. That's all the way back up to the space we started on. So we're starting on the torus, the 1 torus, which means that we associate these points to the same values. These are the quote-unquote same points, which means f of pi and f of negative pi, g of pi, and g of negative pi are the same. So the fact that when you evaluate f and g at those points, you get the same number, that's exactly what it means to be on the torus. And so if you evaluate at the top and subtract evaluating at the bottom, you're getting the same number, so it has to cancel to 0. So that's why I've crossed that term out. And what we're left with is this, which I can simplify a little bit by pulling the minus sign out and canceling with that minus sign. And what we end up with is exactly the inner product of f against I d dx g. And so that's me proving that this operator is Hermitian on the specific space C infinity of the torus, which means that by spectral theorem, I d dx admits a unitary transformation for which I d dx behaves like multiplication. So what I can do is I can construct U and U inverse just by the definition from the spectral theorem, right? So U by definition from the spectral theorem is just the inner product of F against the eigenvalues. What are the eigenvalues, or the eigenfunctions? So what are the eigenfunctions? Of I ddx. It's not too surprising what are the eigenfunctions of d dx. Those are the exponentials. Multiplied by I, that just changes the eigenvalue. But we need to be the exponentials on the 1 torus. So pi and negative pi have to give us the same answer. The eigenfunctions are exactly e to the I n x, right? We actually covered this a couple classes ago. So eigenfunctions are exactly eix. The eigenvalues are in. And so the unitary transformation is the inner product against the eigenfunctions. What is the inner product against the eigenfunctions? It's that. This is the Fourier series transform. We just developed the Fourier series transform only by looking at the Hermitian operator I ddx. We get the Fourier series transform for free using a combination of the spectral theorem and the Hermitian operator I ddx. So that's the Fourier transform. What is the inverse of the Fourier series transform? Well, that's the Fourier series reconstruction. Keep in mind, right, this f hat n is exactly the output there. This is exactly the Fourier series. Because keep in mind, these are our eigenfunctions. So we have a Fourier series and a Fourier series transform that we get for free out of the spectral theorem, just by identifying I ddx as a Hermitian operator. We can then also immediately recover the lovely identity that I first introduced with the Fourier series, and that's just that ddx is a multiplication operator, right? We call these Fourier multipliers. So ddx is a multiplication operator. Underneath the Fourier series transform and its inverse. And so we've really been using this the entire semester in one extremely particular case, or I guess the d-dimensional version works too. And we didn't really know it because, you know, this is a really kind of tricky theorem to develop, right? We've kind of been spending a lot of this last couple of weeks on the spectral theorem. So this theorem is just a more powerful version than the Fourier series and the Fourier transform. That's what we want to think. A more powerful Fourier series, Fourier transform. So where are we headed? We're headed towards the statement here that is my favorite statement in all of PDEs. And actually the physicists love this too, because in quantum mechanics you cannot avoid this. So every Hermitian PDE operator is associated to its own Fourier series. This Fourier series allows for the construction of an associated L inverse, e to the TL, e to the plus or minus TL to 1/2, right? This is the solution to the Laplace's equation, the version of the heat equation that L has, and the version of the wave equation that L has. So we are able to find L inverse e to the TL and e to the plus or minus TL to 1/2 just by constructing a quote-unquote Fourier series for every Hermitian PDE operator. Furthermore, the construction of L inverse may be represented as a Green's function for L. This is how we find Green's functions. We use the spectral theorem to give us a diagonalization. Once we have a diagonalization, we compute d of lambda to the -1, right? This is just 1 divided by the exponential, or the eigenvalues. 1 divided by the eigenvalues. That will give us L inverse, and we can interpret that as a Green's function. So this is how we find Green's functions. I provided in the following proposition. So long as we start with a Hermitian operator, and 0 is not in the point spectrum, right? This was true for matrices as well. You can't have 0 in the point spectrum if you plan on inverting a matrix, but as long as 0 is not in the point spectrum, the Green's function will necessarily be defined by the sum over all of the lambda in the point spectrum. Keep in mind, this is possibly an integral, just from the same caveats as before. But whatever that is interpreted as, the Green's function, all you do is you take the eigenvalues in one variable, right? So the eigenfunctions in one variable, variable y, the left-hand variable, you put those under a complex conjugate, and then you grab the eigenfunctions in the other variable, variable x, that's your second variable here, and you don't have a complex conjugate, and then you also take 1 divided by every eigenvalue. This is the inversion, right? 1 divided by an eigenvalue is now our inversion of L inverse. And then you just sum over all of the lambdas in the point spectrum, and you end up with, right, because every lambda is summed over, this is now just a function of y and a function of x. And so we have g as a function of y and x. That will be my Green's function. And we've got a little bit of a proof here of this, but it's just straightforward, straight out of the spectral theorem. Anyway, that's where I'm going to stop today. I know it's a bit of a longer day, but also my favorite day. This is actually my favorite statement I can make in PDEs, so I hope you like it too. I'll see you in the next class where we'll cover some applications. Bye.